If you are doing any kind of technical or scientific computing, like big data analysis, finance, systems engineering, computational biology, and anything else on this list, then you definitely need to know how to use the MATLAB program. MATLAB is the most common tool for modern interactive scientific computing and complex data visualization. It's widely used in university, academia, scientific research, and professional industries. Where MATLAB really excels is in linear algebra applications. Linear algebra is the branch of mathematics that focuses on understanding and manipulating vectors and matrices, and it is the most important area of mathematics for machine learning, AI, computer graphics, statistics, and data science. In fact, the name MATLAB comes from Matrix Laboratory, so you know that the entire software program is really designed for working with matrices and making matrix manipulations easy, efficient, fast, and powerful. In this video, I'm going to give you an overview of the most important topics in linear algebra that you would learn about in a first semester course on linear algebra. This could be in high school or university, or maybe you're just learning linear algebra on your own. By the end of this video, you will be comfortable with implementing basic linear algebra concepts in MATLAB, including the computations and visualizations. Before we jump in, let me briefly introduce myself. My name is Mike, and this is what I look like. I'm an associate professor at the Donders Institute, which is in the Radboud University in the Netherlands, which is located here. My main job is running a neuroscience research lab where we use cutting-edge equipment to understand the enormous complexities of the brain. We also do a lot of data analysis to look for multivariate spatial patterns, synchronization, neural oscillations, and so on. I also believe strongly in the importance of teaching programming, statistics, data analysis, and math. That's why I write textbooks, and that's why I made this video and hundreds of others like it. You can find all of my courses and books linked from my website here. All right, let's start having fun with MATLAB. The first topic I'm going to cover here will be vectors, because every linear algebra course starts with vectors. A vector is an ordered list of numbers. You can see here there's two numbers, so this is a two-dimensional vector, and those numbers are 1 in the first dimension and 2 in the second dimension. This is the algebraic interpretation of a vector. So you see here is the list of numbers. There's also a geometric interpretation of vectors, and that's to treat these numbers as if they were coordinates on a plane. So you go 1 unit over on the first axis and 2 units up on the second axis. So that can be visually represented by this graph here. So 1 unit over and 2 units up. So now we have this representation of a vector and this representation of a vector. Now let's see how to implement vectors like this and like this in MATLAB. So here we go. I'm creating a 2-element or 2-dimensional vector. We're going to call this variable v1, and I'm using square brackets here to concatenate these two numbers into a single vector. So I'll run this line by selecting this text, right-clicking and pressing Evaluate Selection. Now, because I added the semicolon here, that's going to suppress the output, so it doesn't report back what that variable is. I can do that manually by typing v1 and then enter. So you can see that v1 is equal to 13. Not so interesting, considering that's exactly what I wrote here. You can also type whos, and that will list all the variables that are stored in MATLAB's workspace. So I can see that there is exactly one variable, because I only created one variable. That's called v1. It is size 1 by 2, so that means it's a row vector. 1 row and 2 columns, so that's what this indicates here, the geometry. And sometimes this information is useful about the variables, and sometimes it isn't very useful. So this is the class, it's double. That basically just means it's a number that can have some decimal points after it. So this is the vector. Now I'm defining a scalar. A scalar in linear algebra is just a single number. In this case, I'm picking the number 2. Here I'm going to open up a new figure. And whenever I open new figures, I like to type CLF, which stands for clear figure. That just makes sure that we're working with a fresh, clean figure with nothing already in it. So there we go. Here's our figure. And now I'm going to draw something in here. What I want to draw is the vector as a line. So let me first draw this vector. And now I will explain how I got this line. To create a line in MATLAB, you need to specify the start and the end coordinates for x and the start and end coordinates for y. So I want this vector to start at the origin 0, 0. And how far should it go out on the x dimension? It should go 1 unit, so that's v1 and then the first element of v1. And then along the y dimension, I want it to go from 0, here the origin, up to, in this case 3, but it's really whatever's the second element of this vector v1. So this is the core part of the plot function in MATLAB. Here I'm specifying some additional inputs. This is going to make the line color set to black, and this will set the line width to be 3, so that's going to be a thicker line. I'll just change these parameters a little bit to give you a sense of the variety. So I can make this line width 1, and I can make this a, let's say, a green line. And now I'll run this line again. So now the line is thinner. It's actually a little bit hard to see, but I hope you can make it out. It's a thin green line, and that's what I specified here. So if you would plot this line and then run the plot command again, that's actually going to overwrite the previous plot. So we lost that black line. But I want to have the black line and this red dashed line on top of each other. So therefore, I'm using the hold on command in between them. And that will plot both of these lines together. So what is this thing that I'm plotting here? Well, I take exactly this same vector. So I'm plotting the same vector, but now I'm multiplying it by this number in variable s, which is called a scalar. And now you can see why in linear algebra a single number is called a scalar. It's called a scalar because what this scalar is doing to this line, this vector, is scaling it. It's making it longer. In this case, it's stretching it. So the line doesn't change directions when you multiply by a single number. It doesn't point over here. It doesn't point around here. It's not changing direction. It's staying on this line, but it's getting a little bit longer. Well, in this case, it's getting twice as long. So here you see these two vectors. I don't think this plot looks very nice. For one thing, this is supposed to be the origin of the plot, but it's down at the lower left corner. So I think it would be good if we would change the axes of this plot so that the origin would be at the center. That's the way you would typically expect to see a plot like this. So to do that, I'm going to use the set function. And the idea of the set function is that you input first the handle to the property that you want to change. In this case, it's GCA, which stands for get current axis. So this is the axis. This is the figure, this whole gray thing here. This is the figure. And this is one axis that's embedded inside the figure. So the handle is always the first input into the set function. Thereafter, you always input pairs of inputs, and they are called property value pairs. So property and then value, and another property and value, and you could list even more properties and their values that you want to change. So here I'm changing the xlim, that's the x limit, and now I'm setting it to this vector, -1 to 1, times, this is going to be a variable, a single number, xlim, so I'll explain what this line does in a minute. So I change the x limit, and then I change the y limit. And what I want to do with this line is set the x and y axes to go from minus something to plus that same thing. So I could say, -2 to +2. That would give me a plot that would go around like this, but you can see that these two lines would be outside the range if I went +2 to -2. So I want to make sure that whatever you set these values to, and whatever you set this scalar to, those lines will always be in the axis. And that's what I'm doing here. So I'm using this function norm, which extracts the so-called norm of the vector, or it's also the length of the vector. It's basically how long this line is. So whichever is longer, the original vector or the scalar multiplication with the vector, that's what I want this limit to be. So in this case, with these numbers, the norm of the longer vector ends up being 6.3, and so that's what I want to set these axis limits to. So now this is good. We have minus something to plus something on the x and y axes, so it's going to be a square, and the origin is exactly in the middle. This is the kind of graph that you would expect to see. Okay, now I'm going to turn the grid on. You'll see what this does. That puts this nice grid on the back as if we're working on engineering paper here. And now this line, axis square, that just enforces that the axes will be square. And that's because you can see if I stretch out this figure like this, then this is no longer square, it's a rectangle. But that's not really the way you would expect a plot like this to be drawn. You want it to be a perfect square. And by typing axis square, this figure will remain a square, or I should say the axis will remain a square, regardless of how you stretch this figure window. So this is almost perfect, I think. What I want to do now is plot thick lines on the 0 axes. So I want to draw black lines that go from all the way the left edge to all the way in the right edge along this 0 line, and then same thing here, all the way from the bottom edge to all the way from the top edge. But how do you know what is the top and bottom edge and left and right edges of this plot? So we kind of computed it here, but this is not really the best solution for drawing these lines because you don't always draw these here. So what I'm going to do is the complementary function to set. So I just told you about the set function. Now I'm going to use the get function. It's kind of similar. You can see it's get, and then the first input is the handle to the drawing feature that you want. So that's get current axis. So again, that's this axis. But now there aren't pairs, there's just a single parameter, and this is xlim. So when I run this piece of code, this is going to return the x-axis limit, so from minus 6.3 to plus 6.3. Now, as I mentioned, in this particular case, that ends up being already this variable xlim here. And that's because that's what I set the xlim and the ylim to. But I like this approach because this is a little bit more generic. This is something you can always apply to all of your graphs, whereas this really is designed for this specific case. Okay, so the x coordinates are going to be these, so the beginning of the x and the end of the x, and then the y coordinates will be 0 and 0. And this is how you draw a flat line in MATLAB. Now I'm going to set these to be black line, and they're going to be dashed. And here I do the same thing for the vertical line at the origin. You can see it's almost exactly the same as this line, but the order is swapped, and now I'm getting the y limit instead of the x limit. So let me run these. Actually, this hold on here is a little bit redundant because I already typed hold on here. So this looks kind of nice, but you know, maybe I regret making these lines be black. Maybe I want them to be light gray instead of black. So you can change the color of these lines by assigning an output to the plot function. You'll notice here I didn't assign an output to the plot, I just ran the plot function. Here I'm saying this variable h equals plot. So let's see what this variable h ends up being. There's two of them actually. So you can see it's 1 and 1. And these are two lines. So let's just look at the first one. These are handles. So here I showed you a handle to the current axis. You can also get a handle to a specific line. And here you see what that handle looks like. There's all these properties that are associated with this particular handle, which is this particular plot line. So there's the color, the line style, the line width, and so on. There's many, many properties. And what I want to do now is set from the handle, and actually I can input a vector of handles here, and I want to set the color. And what do we want to change the color to? So I'm going to list three numbers that corresponds to R, G, B. They have to be scaled between 0 and 1. And in this case, I'm going to make it 30% of white. So let's see what effect that has. So here they are black, and now they are light gray. So it's not totally visible. I mean, it's not a huge change, but they are a little bit lighter now. So I've been talking a lot about MATLAB code. I want to talk a little bit more about linear algebra concepts. This is a really important concept. It's a very simple concept, but it's really important in linear algebra, that when you multiply a vector by a single number, that vector doesn't change direction at all. It gets longer, maybe it gets shorter. I can show you what it looks like when it gets shorter. So let's make this 0.2 instead of 2. So now here is the original line, and now here is the scalar multiplied version of that line. It got shorter, but it's still pointing in the same direction. Now there's one confusing thing about this, which is if you set the scalar to be negative, you might initially think that this is a different direction because it's kind of pointing backwards. But really the way to think about a vector in linear algebra is that there is an infinitely long line that goes along this direction. It goes infinitely far down here and infinitely far up here. In fact, there is a term for this, which is a subspace. There is a one-dimensional subspace, which is this line. It goes infinitely far, infinitely far. So in that sense, multiplying by a negative number, having a negative scalar, is not changing the direction. It's just pointing it the other way on this one-dimensional subspace. The reason why this concept is so important is that it turns out to be the basis for a procedure called eigendecomposition, or sometimes called eigenvalue or eigenvector decomposition. Eigendecomposition is one of the most important concepts in linear algebra for machine learning and classification and artificial intelligence, and it really all comes from this simple concept that you can multiply a vector by a single number and that doesn't change its direction. All right, now I want to show you how to plot vectors in 3 dimensions. So first we had a 2-dimensional vector. Now we have a 3-dimensional vector, so there's 3 elements in this vector. In fact, I'm creating 2 vectors. One is this here, where I'm specifying the numbers, and here I'm generating random numbers. So in this case, I'm using the function rand_n to generate a matrix that's 1 by 3, so I can show you what that would look like. So 3 numbers in a row. These are random numbers, so if I run this code again, you'll see the numbers keep changing. And then I'm multiplying that by 5 just to scale them up a little bit, and then rounding them. So this is one way in MATLAB to create a bunch of random integers. You can see these are all integers because they're being rounded, and every time I run this line, I get a new random vector. Now I'm plotting almost exactly the same way as I did in the previous cell, but I'm using the plot3 function instead of the plot function, because here I actually want to generate a plot in 3 dimensions. So these are the x boundaries of the line, the y boundaries of the line, and now we also have to specify the z boundaries of the line. A lot of the rest of this code is really the same as what I showed in the previous code. So here's what that looks like. And now you can left click and drag and rotate this 3D space around to get a better impression of where these 2 lines lie in this 3-dimensional plane. This rotation is done by typing rotate 3D on. Now I want to show you about matrices. A vector is a list of numbers that's oriented either in a row or in a column. A matrix is like taking a bunch of vectors and putting them all together. So you could think of this matrix as being 3 vectors, 3 column vectors that are compressed into one item, one thing. Or conversely, you can think of this as being row vectors, and then I have 4 of them, and those are all put into one unit. I can type whos again in MATLAB, and now you can see, let's see, so these were the vectors that we created. So it was 1 by 2, 1 by 3, and the matrix is called AMAT for a matrix. And now you see the size of this is 4 by 3, and that you see here. So it's 1, 2, 3, 4, so there's 4 rows, and then 3 columns like this. Now, it's not so convenient to plot matrices in a graph like this. Instead, the better way to visualize a matrix is using an image or treating the matrix like an image. So let me show you what that looks like. So here you see the numbers. Let me dump this out again. Here are all the numbers, and if you map these numbers onto colors, then each element in this matrix corresponds to a different color. And you can see how these are mapped. The darker colors towards red correspond to larger numbers, and deep blue colors here would correspond to smaller numbers. So this green color here means that these are numbers that are in the middle, in between the lowest number and the highest number. So this is a random matrix. There are several special matrices that are really important for linear algebra. One special matrix is called the identity matrix. It's given by the MATLAB function I, which is pretty cleverly named. And the identity matrix is the matrix equivalent to the number 1. So you know that the number 1 is really special because any number times 1 is that same number. Same thing for the identity matrix. Any matrix times the identity matrix is that same matrix back. So these are all zeros and they're all ones on the diagonal. That's what this line down the diagonal is called. This is called the matrix diagonal. So these are all zeros, these are all ones. I can dump this out in the command so you can see. So a matrix of all zeros here and ones on the diagonal. Here I'm generating another random matrix just to show you that these matrices can be even larger. This one looks pretty neat. This is like colored static on an old TV screen or something. There's many other kinds of special matrices that you will encounter throughout your adventures in linear algebra. One is called a triangular matrix. And let me first show you what the triangular matrix looks like. So it has all elements above the diagonal. So remember, this is called the diagonal. The matrix can have non-zero elements above the diagonal, but crucially for an upper triangular matrix, all the elements below the diagonal are set to 0. And that's what happens when you input a full matrix into this function trie_u. So this is the triangular, and this extracts the upper part of the triangular matrix. Now you might be wondering if there's a complementary lower triangular matrix, and the answer is absolutely there is. And you just replace the u with an L for lower. So let's see what this one looks like. So this is the lower triangular matrix. Now all of the elements above the diagonal are 0, and all the elements below the diagonal have some non-zero values. Here I have a three-dimensional axis. So this is one axis, and this one you have to imagine is like sticking out of the monitor coming towards you. So if you have three-dimensional vectors, you can plot those as lines in this three-dimensional space. So one of the really interesting things that you can do with two vectors that are not pointing in exactly the same direction, so two distinct vectors, is form a plane. Now, it's not so obvious from looking at this picture that this plane is formed by these two vectors, so that these two vectors are in this plane. But you will see this more clearly when I switch to MATLAB in a few minutes. So how do you create a plane from these two vectors? Well, the idea is that if you would take these two vectors and add them together, that would give you some point. It might be a point that's over here. And then if you would take some scaled version of this vector plus some scaled version of this vector, that would give you some other point, and that would be, I don't know, maybe it would be here. Of course, it depends on which values you pick for the scalars for this vector and this vector. And if you would take lots and lots of random combinations of these two vectors, so basically you multiply this vector by a scalar and add it to this vector times some scalar, you would find, amazingly enough, that all of the points that can be reached by these two vectors would form a plane. They would form a two-dimensional plane. It's like a piece of paper that's infinitely long in all directions. So this is not a real boundary. This is just the boundary that I'm showing here. It goes infinitely far in this direction, this direction, this direction, and this direction. And this is what is meant by the term span. So you could say that two vectors, if they are linearly independent, two vectors span a plane. Now in this case, because there are two vectors, and this is 3 dimensions, this is a two-dimensional plane that's embedded in an ambient 3-dimensional space. So how can you create this plane? Well, one way to do it is to compute an operation on these two vectors, and that's called the cross product. And the cross product of these two vectors will be a third vector that is orthogonal to, or is at right angles to, every point in this plane. And that is the key to describing this plane, because once you know this cross product, then you know that every point in this infinitely long plane must be orthogonal to this cross product. Okay, so now we've created a plane, but what do you do with the plane? One of the interesting questions in linear algebra, particularly in applied linear algebra, is whether some other vector is contained in the span of this plane. So let's say this red vector here. We want to know, is this vector on this plane? Now remember, this plane, it goes out infinitely far in these directions, but it's infinitely thin. This is an infinitesimal plane. It doesn't have any thickness. So does this red vector lie in this plane, or does it point off from the plane a little bit? Like this blue vector is pointing off. In fact, this blue vector is pointing orthogonally to the plane. Now, you don't really see from this view, this angle, whether this red line is actually really truly in the plane. But this is an important question. In fact, when you learn about statistics, there is a geometric perspective of statistical models, linear models, and that is really all about determining whether a vector is in the plane spanned by other vectors. And then if this vector is in the plane, you want to know what is the combination of this vector and this vector that will produce this vector. And if this is not in the plane, let's say, maybe you don't see it exactly from this view, but let's say this vector is not touching this plane, it's kind of pointed up just a little bit. Then you want to know how close is this to the plane, and what is the point in this plane that is as close as you can possibly get to this vector without leaving the plane. These are all really important concepts for applied linear algebra, particularly in statistics. All right, so this is a bit of theory, and now I want to switch to MATLAB to show you how to produce a graph that looks something like this. So here I define two vectors. These are two 3-dimensional vectors, so there's 3 elements. In this case, I'm transposing the vectors because I want them to be column vectors. So if I would run it like this, then this is going to produce a row vector, and then I transpose this, and the transpose operation will convert a row vector into a column vector. So it's the same numbers, but now it's going up, down instead of going left, right. Okay, so here is our 2 vectors, and these are going to be the 2 vectors that define the plane. So in order to create this plane, I need to compute the cross product between them, and that's a third vector that is orthogonal to these 2 vectors. So I'm using the MATLAB function cross. Now this is just some vector. It turns out that, let me run this code here. This is just some vector. It turns out that we don't actually care about how long this vector is. This vector can be really, really long, or it can be really, really short. All we need to know is the direction that the vector points in. We don't care about the length of this vector, we just want to know its direction. So therefore, I decided to normalize this cross product vector to be unit length. So now I'm using the norm function, so we can already see what is the length of this line. So the magnitude of this vector is 33, and that number is just related to these individual elements. In fact, 33.6 is 21 squared plus 4 squared plus 26 squared, and then the square root of that sum. So that is the magnitude or the norm of this vector. But I want to make this a unit normalized vector. So I'm going to divide the vector, divide each of the elements in the vector by the norm, and you will see that that gives us different numbers Remember up here, these were the numbers minus 21, 4, 26, and now it's minus 6, minus 0.6, 0.1, and 0.77. Now, it's not so obvious just from looking at the numbers, but it turns out that this is a unit vector that points in exactly the same direction as this vector. So now that it's a normed vector, it's a unit vector, I can type norm again. We can look at the norm of this vector. And now it's exactly 1. So this vector is now 1 unit long. So here I'm plotting these 3 vectors. So the first 2 vectors that I specified here, plus the cross product that I computed. Let's already plot this. Now, so far it's kind of hard to see where the plane is going to be. It's certainly going to include these 2 vectors here. And it's not going to include this red vector. I'm going to use the function EasyMesh to create a mesh or a plane that is spanned by these 2 vectors that we specified earlier. So I'm using a pretty neat, slightly advanced MATLAB programming tool here called anonymous functions or inline functions that's indicated using the @ symbol. And so essentially what I'm doing is setting up a system of 3 linear equations that's going to define the x coordinates, the y coordinates, and the z coordinates for all 3 of the dimensions. Let's see what this looks like. So here we have the 2 vectors. This is the 3rd vector. Now this figure to me really highlights the power of using MATLAB for learning about mathematics, and in particular linear algebra, and in particular learning the connection between geometry and algebra. And that's because if you saw this picture in a textbook, you wouldn't really get a good sense, or maybe you would kind of understand what's going on if you have a really great imagination, you have a good visual imagery. But here in MATLAB, it's much easier to understand what's going on because you can just click and rotate and move this picture around. And now you really see that this plane is exactly going through these 2 vectors. And this red line, which is the cross product, is going right through it. It's orthogonal to this plane. Now, I strongly encourage you to download this script where you're watching this video from and change these numbers, and that will change all of these 3 elements. The plane, the 2 vectors that define the plane, and the cross product. I mentioned in the slides that one of the important questions in linear algebra is whether some vector is in the column space of a matrix. Now, the geometric picture is whether we can draw another vector that is also exactly in this plane, just the way that these 2 black lines are exactly in this plane. Now, asking this question geometrically is useful for 2 dimensions or 3 dimensions, but in linear algebra, we want to be able to ask the same kinds of questions for, let's say, a 25,000 dimensional matrix. Now, I have no idea what a 25,000 dimensional space looks like. We're certainly not able to draw it here in MATLAB. So therefore, we switch to algebra. And in algebra, one of the ways that you can ask whether a vector is in the column space of a matrix is by concatenating the vector into the matrix and then computing the rank of the matrix. The rank of a matrix is a single number. It's an integer. It's a non-negative integer, so it's 0 or higher. And it tells you about the dimensionality of the information that's contained in the matrix. So for example, if you would put these 2 vectors, these 2 black vectors, into a matrix, the rank of that matrix would be 2 because we have a 2-dimensional space of information. And if I put another vector into that matrix that was still in this green plane, the rank of that matrix would still be 2 because that other vector is still inside this plane. Now in contrast, if I put this red vector inside the matrix, that would have a rank of 3 because this red vector is pointing off of the plane. So this red vector is not redundant with the geometric directions that are defined already by these 2 black vectors here. So algebraically, we're going to do the same thing. Here I'm creating a matrix. Let's have a look at this matrix. So you can see it's a 4 by 3 matrix, and it just has a couple of random integers that I picked here. And now here I'm creating two additional vectors. These are both column vectors, and these are constructed such that they will fit concatenated into matrix M. So here's the matrix M, vector v1, vector v2, and I can concatenate them to create an even larger matrix here. So this is the original matrix M, and here I'm concatenating vector v1 onto the end of matrix M. So now an interesting question is whether v1 or v2 are contained within the column space of matrix M. And again, the picture is whether v1 or v2 would be inside the plane that's spanned by the columns in matrix M. Now I've given you a little bit of a cheat here because it turns out that I created this vector by the first column of M times 2 minus the second column of M times 3 plus the third column of M. In fact, we can even confirm this here. So we do a little bit of algebra, and we get minus 1, 1, 5, 6, and that's exactly this vector here. So here I told you the answer. So we know that this vector is already inside the plane that's spanned by these three columns. But how about v1? I didn't give you any hints or cheats here. So is this vector, are these four numbers computable by some linear combination of these three columns? So the way that I'm going to do this is by computing the rank of the matrix with that extra vector concatenated after the matrix. So let's first see what the rank of M is. The rank of M is 3, and there's 3 columns. So that means that there are 3 independent vectors. These column vectors are all pointing off in different directions. So you can think of the column space of M as like a plane, except it's a plane in a higher dimensional space. It's somehow a 3-dimensional plane in 4 dimensions. I don't really know what a 3-dimensional plane in 4 dimensions looks like, but somehow it's like a cube that goes infinitely far in all directions, but it still doesn't cover the entire space. So because vector v1 is inside that column space of M, or in the plane of M, then adding v1 onto the matrix is not going to increase its rank. Sorry, I meant to say v2. So the rank of matrix M concatenated with v2 is still 3, even though the size is larger. So we can see the size of matrix M is 4 by 3, but the size of matrix M concatenated with v2 is 4 by 4. However, the rank is the same with or without adding that other vector. And that indicates that this vector does not add any unique information to M that wasn't already present in M. Now in contrast, when we run this line, so the rank of M concatenated by vector v1, now the rank goes up to 4. And that tells us that v1 is providing new, unique information that wasn't already present in M. So that means, geometrically, that vector v1 is sticking out from that 3-dimensional hyperplane that's created by all of the combinations of these 3 columns. I would like to talk a little bit more about rank. Here I'm creating a 2 by 2 matrix. And this is called a singular matrix. And a square matrix that has reduced rank, so when the rank is lower than the total number of columns or the total number of rows, then that matrix is often called singular. And singular means that the matrix does not have an inverse. If you are not familiar with the concept of the matrix inverse, then you're in for a special treat, and I will tell you all about the matrix inverse in a few minutes. So you can look at these numbers and you can see that this column is a scaled version of this column. So this is 1, 2, and of course 1 times 3 is 3, and 2 times 3 is also 6. So this column is basically this column times 3. You can also look at it row-wise. So if you multiply this row by 2, you'll get exactly this row. So that means that there's really only one dimension of information in this matrix. There's 2 columns and 2 rows, but there's really only one dimension because this row is a scaled version of this row, or you can think of this column-wise. So that means that although this is a 2 by 2 matrix, the rank of this matrix is just 1, and we can confirm that here. So this is called a reduced rank matrix. You can see in contrast, if I would change this to 7, now this times 3 is 3, but this times 3 is not 7. So this column is no longer a linear multiple of this column. So now the rank of this matrix is 2. All right, so let me go back to this reduced rank matrices. One thing about reduced rank matrices is that they have a determinant of 0. It also means that they don't have an inverse, in part because computing the inverse of a matrix involves dividing by the determinant, and you cannot divide by 0. One way to create a reduced rank matrix is by multiplying two matrices together, where the inner dimensions, so this dimension and this dimension, are smaller than the outer dimensions, which is 30 and 32. And what's going to be interesting about this matrix is that the size will be 30 by 32. So let me show you this. So the size of this matrix is 30 by 32. However, the rank of this matrix is going to be 4 because we're actually only getting 4 dimensions of information in this matrix. So it's a big matrix, 30 by 32, but the rank is only going to be 4. Now I'm going to show you what these different matrices look like. So here's a tall, skinny matrix, and here's a wide, fat matrix. And when you multiply these together, you get a larger matrix. And this matrix contains information that is mixed between this matrix and this matrix, but it has a small rank, much smaller than the sizes of the matrix. So here's a pretty simple equation. I'm sure you can solve this one in your head. If you want to know what x equals, you would divide both sides of the equation by 3. That's probably how you think about this, dividing both sides of the equation by 3. But I would like to propose a slightly different way to interpret this question. Instead of dividing by 3, what if you multiplied both sides of this equation by 3 to the power of minus 1? Now, that's the same thing as 1/3. It's the same thing as 1 divided by 3. It's just a slightly different way of writing it. So if you would multiply both sides of this equation by 3 to the power of minus 1, then here you have 3 and then times 1 over 3. So those cancel, and this becomes 1. So this is 1x. And then this equals 1 times 3 to the minus 1. And of course, we can just drop the 1s because anything times 1 is that same number. All right, so that's pretty clear. What is the matrix version of this kind of equation? So it looks like this. We have matrix A and matrix X equals the identity matrix. And remember I said earlier in this video that the identity matrix is the linear algebra equivalent of the number 1. So how do we solve for X? Well, we follow the same procedure here. So I'm going to multiply both sides of this equation by a to the minus 1. So that's going to look like this. So we have the same concept as here. A to the minus 1 times a. These will cancel out just like 3 times 3 to the minus 1 will cancel out. And this leaves us with the identity matrix over here. And then we have the identity matrix times a to the minus 1. And again, we can just drop the identity matrix because that doesn't change this at all. So that leads us to this conclusion that x equals a to the minus 1, and this is called the inverse of a. So in this equation, you would say that x, matrix X, is the matrix inverse of matrix A. This is really important because this allows you to solve equations using matrices. Now, what's tricky about this equation is that not every matrix has an inverse, so it's not always possible to come up with some matrix such that that matrix inverse times the original matrix gives you the identity matrix. That's quite different from normal algebra, where any number except for 0 has an inverse. So here, that's not necessarily the case. So when matrices have an inverse, they're very special, and they are called invertible or non-singular. Or they're called full rank. And you already saw this idea of rank. A matrix is invertible. A matrix has an inverse if it is a square matrix and if it's a full rank matrix. Let's have a look in MATLAB. So here I create a square matrix, so it has the same number of rows and columns, and this matrix looks like this. Now I know, because I wrote that this matrix is invertible, then that means that the rank of this matrix should be equal to the number of columns, which is also equal to the number of rows. So I can say rank of A, and that should be 3. If this weren't 3, if this were 2 or 1, then it would mean that this matrix does not have an inverse. And I'll show you what that looks like in a minute when we get here. So now here is the inverse of A. I'm using the MATLAB function inv to generate the inverse of matrix A. Now the inverse is a little bit tricky to compute. It's a little bit involved. It's not as intuitive as you might think. You might expect or you might hope that the matrix inverse would be the inverse of each individual element. So this would be 1 divided by 1 and 1 divided by 2, 1 divided by 3, but unfortunately it's not quite that simple. However, MATLAB will take care of all of those boring details for us and just return the inverse of this matrix. So what I'm going to plot here is the matrix A, its inverse, and then the matrix times its inverse. And this should equal the identity matrix. So let's run all this code. Here we go, the matrix A inverse, and the matrix A times its inverse. And you can already see that that looks like the identity matrix. So it looks like 1s on the diagonal and 0s off the diagonal. And that is indeed what this ends up being. So 1s on the diagonal and 0s off the diagonal. This is a little bit funny looking here. This says -0. But that's just because there's probably some really tiny computer rounding error that's at 10 to the -15 or something. Now, not every matrix has an inverse, as I mentioned. A matrix needs to be square, and it needs to be full rank in order to have an inverse. So here's the matrix. It is square, so that satisfies one of the conditions for invertibility of a matrix. But if you look at the rows of this matrix, you'll see that this row plus this row equals this row. So in fact, the rank of this matrix is 2, and we can confirm that by typing the rank of this matrix. So the rank is 2 because these two columns are independent of each other, but this column you can get by some combination of this column and this column. Sorry, I keep saying columns, I meant rows. But that doesn't mean that this is the weird row and we should kick this out. You can create this row from a combination of these two rows. So now, because the rank of this matrix is smaller than the number of columns or the number of rows, this matrix is not invertible. And that you can see here when I try to compute its inverse. MATLAB is going to give me a warning. It'll say the matrix is singular to working precision. And then it says that the inverse is just a matrix of infinity, which is a pretty neat concept, that you have a matrix of multiple infinities, but unfortunately that's not very helpful. Now there's an interesting computation that you can apply called the pseudo-inverse. So every matrix has a pseudo-inverse, even if it doesn't have a full inverse. The pseudo-inverse is basically as close as you can possibly get to the full inverse for a matrix that doesn't actually have a full inverse. You can use the MATLAB function pin for pseudo-inverse. Now you'll notice that this didn't give me any warnings like this did, and this is a real matrix. It has actual non-infinite values in this matrix. So now I'm going to generate the same plots that I did up here, except this is the pseudo-inverse and not the full inverse. So the full inverse is indicated using a -1 in the superscript, but here this is not the full inverse, so people typically use either a star, an asterisk, or a dagger sign. So here you can see the matrix times its pseudo-inverse. This is almost the identity matrix, but it's not actually the identity matrix. Because this matrix is singular, because it's reduced rank, there is no possible matrix that exists in the universe that can multiply this matrix to give the identity matrix. The best we can do is to come up with some approximation that will get us kind of close to, but not exactly the identity matrix. And that's this matrix here. So let's have a look and see what this thing looks like. So you can see that it's wanting to be the identity matrix. The values on the diagonal are larger. The values on the off diagonal are smaller, but it's clearly not exactly the identity matrix. If I gave you an equation like this, could you solve for x? Yes, of course you could. It's a little bit of algebra. You would subtract 3 from both sides of the equation. That would give you 2x equals 2. And then you divide both sides of the equation by 2, and you'd find out that x equals 1. In fact, you don't even need to go through all the algebra. I think here you can just kind of eyeball this equation and see that 2 plus 3 equals 5, so therefore x must be equal to 1. Now, how about this system of equations? So if I told you that these two are related to each other, so there was one common solution for these two equations, could you come up with a solution just by eyeballing? Perhaps you could if you're really good at this or if you're staring at it for a really long time, but I think it would be quite difficult. It's quite a challenge. And what makes this even more challenging is there's not only one solution to this system. In fact, there are many solutions. There's an infinite number of solutions to this system. And that's because there are more unknowns than known. So there's 2 equations, but 3 unknowns, 3 variables. In your algebra course, this can be a little bit tricky to solve. But in linear algebra, in matrix analysis, this is actually quite easy to solve. And the way you do this is by transforming this system of equations into its matrix form, and that would look like this. So basically you separate all of the coefficients, which are these numbers that are multiplying the variables, put those into a matrix like this, take all of the variables here, these unknowns, and put them into a vector like this, and all of the constants, which are any number on the right-hand side of the equation, or any number that's not attached to these variables. You put those all into the right side of the equation. Like this, you would put the 3 over here. And those go into a vector on their own. Then we rename these as ax equals b. So that would look something like this. Now you might see this with different letters, but that's okay. It's the concept that's important. So the matrix of coefficients times the vector of variables times a vector of constants. And now how do you solve this equation? So one way to do this is by multiplying both sides of this equation by A inverse. That would look something like this. That's a pretty clear solution because you have x equals A inverse times B. But in this particular example, matrix A actually does not have an inverse. This is a non-invertible matrix. And that's because it's not square. Remember that the 2 qualifications for a matrix having an inverse is it has to be square and it has to be full rank. So this matrix is not square. So it doesn't have an inverse. However, we can still follow this same procedure. A has something called a right inverse, a one-sided inverse, that we can use in this particular equation. So what I'm going to do now is show you how to solve this system of equations in MATLAB using matrix notation. Okay, so here is a system of equations. I got these numbers from Wikipedia and the page on systems of linear equations. So you can look up the wiki page for systems of linear equations and you will find this as an example. So now to solve this, I'm going to use matrix algebra. So as I said in the slides, the first thing to do is to separate the coefficients, that's the numbers multiplying the variables, and you put those into a matrix. So this corresponds to x, y, and z. Now you have to be a bit careful here that if it's just z on its own, then that's actually -1 times z. And then this is for the second equation. This is for the third equation. And then I have the vector of constants, and this is what's on the right-hand side of the equation. So this is a matrix. This is a column vector. I'm specifying this as a row vector, but then I transpose it. So now this becomes a column vector. And now the solution is given by the inverse of the inverse of the coefficients matrix times the constants matrix. This is exactly the formula that I showed in the slides. Now in this case, this coefficients matrix happens to have a full inverse, so that allows me to write out this formula like this. But you can already see MATLAB is giving us a warning here. It says, explicitly multiplying by the inverse can be slower and less accurate, so consider using a/b. And that's this operator here. So MATLAB is saying we should use a/b, and that's essentially this, so a/b. And the great thing about this slash operator in MATLAB is this will work even if there is no explicit inverse. MATLAB will know to compute the one-sided inverse, or it uses some other more advanced tricks in linear algebra to come up with a solution. But this is conceptually the same thing as multiplying by the inverse. So let's see what this solution is. Oops, let me run this code here. So this solution is 1 minus 2 minus 2, and that's the same answer we get if we run this code, 1 minus 2 minus 2. And you can look up on Wikipedia, you can go back to this page and confirm for yourself that the solution to this system of equations is x equals 1, y equals minus 2, and z equals minus 2. Now I'm going to tell you about eigendecomposition and the eigenvalues and eigenvectors of a matrix. Eigendecomposition is one of the most important operations in all of linear algebra. It has huge applications both for theoretical, more abstract concepts in linear algebra, and definitely for applied linear algebra. And if you're doing data analysis, if you're interested in machine learning or statistics or data compression or computer graphics, you definitely need to know all about eigendecomposition. When I teach linear algebra, I always start with eigendecomposition using 2x2 matrices, because that allows me to plot the eigenvectors and eigenvalues, and that gives you a visual sense of what eigenvectors mean, why they're so important for a matrix. So first of all, let's look at this matrix. It's a 2x2 matrix. It's a full rank matrix, which means it's also invertible. So if you want to get from this column to this column, you could multiply this element by 4, but of course 5 times 4 is definitely not minus 2. So that means that the columns are linearly independent of each other, which means the rank of this matrix is 2. Now that is not a requirement for eigendecomposition. You can take the eigendecomposition of any square matrix. It does have to be square, but it doesn't have to be invertible. And it doesn't matter what the rank is. Okay, so if you use the MATLAB function eig of matrix A, that's going to return the 2 eigenvalues for this matrix. Now, for a square matrix, however many columns you have, which of course is the same number of rows that you have, that's the number of eigenvalues that you get. So this matrix has 2 columns, and therefore it has 2 eigenvalues. Now that's what the output of the eig function is if you only request one output, or in this case, no outputs. What we want here is both the eigenvalues and the eigenvectors. So therefore we need to use 2 outputs of the eig function. So let's see what those 2 outputs are. So the eigenvex, what I call here eigenvex, that's the matrix of eigenvectors. And those are the eigenvectors in the columns of this matrix. And now the eigenvalues are in the diagonal, so that it's the same 2 numbers here, except that now these are in the diagonal elements of diagonal matrices. So the off-diagonal elements are zeros, and the diagonal elements correspond to the eigenvalues. So this is the eigenvector that corresponds to this eigenvalue. This is the eigenvector that corresponds to this eigenvalue. Now, to show you how to interpret these eigenvectors, what these eigenvectors mean, what I'm going to do is create another vector that is not an eigenvector. So this variable is not evec. So 2, 1 is not an eigenvector. You can see that by looking at these columns here. Okay, and then here I'm just normalizing it to be a unit vector because these eigenvectors are also unit vectors. Now what I'm going to do is come up with two new vectors, and these two vectors are defined as the matrix times the eigenvector, or the matrix times not an eigenvector. So let's see, and then I'm going to plot them. So this is just plotting the eigenvector, and then plotting v, which is the matrix times the eigenvector, and this is plotting the not an eigenvector, and w, which is the matrix times that not eigenvector. Okay, so here's what this graph looks like. Now, this black line shows an eigenvector, and the dashed black line shows the matrix times the eigenvector. This red line shows a vector that is not an eigenvector, and the dashed red line shows the vector that is defined by the matrix times that vector, which is not an eigenvector. And what is the difference between the black pair and the red pair? The difference is that when you take an eigenvector and you multiply it by the matrix, the resulting vector is exactly the same. This is really just a scaled version of this same vector. So we took this vector, multiplied it by the matrix A, and it didn't change the direction. It just got longer. Now, it doesn't always have to get longer. It might get shorter. It might point in this direction here. But you'll remember in the very beginning of this video, where I talked about vectors and scalar multiplication, I said that scalar multiplying a vector won't change the direction of the vector. It only makes the vector a little bit longer or a little bit shorter. And that's exactly what we see here. We multiply the eigenvector by a matrix. Now, this is not a scalar. This is not a single number. This is an entire matrix. And yet, multiplying this entire matrix by this vector is behaving as if the entire matrix were just a single number. And that is what is so special about eigenvectors. Now, you take this vector in contrast. This is not an eigenvector. So when we multiply it by the matrix, it's going to point off in some other direction. And I knew for sure, before I even started writing this code, that this vector times the matrix will produce some other vector that points off in some other direction. I didn't necessarily know that it would be this direction. Maybe it would point here. Maybe it would get a little bit smaller and point off in some direction. But if a vector is not an eigenvector, then multiplying that vector by a matrix will absolutely change its direction. It will make the vector point off in some other direction. Whereas if that vector is an eigenvector of the matrix, then multiplying by the matrix will just stretch it or shrink it. The entire matrix is just behaving as if it were a single number. That's a pretty remarkable concept. Now, in this case, the matrix is 2 by 2, and it's acting on this eigenvector as if it's a single number. Now, maybe you're not so impressed by that, but imagine that this matrix were 10 million by 10 million. This is like the size of matrices that Google is dealing with when you're typing in search terms. These are millions of columns in these matrices, and yet those matrices, which might have trillions of numbers in them, when they multiply the corresponding eigenvector, that huge matrix is behaving as if it were a single number. And that is why eigenvectors are really important. They highlight the important features inside a matrix that are invariant to rotations. If you look at this slide and you feel intimidated and a little bit overwhelmed, then that is completely normal. This slide shows the big picture of the SVD, or the singular value decomposition. The SVD is one of the most important and versatile decompositions in all of linear algebra. It's also a fairly advanced topic in linear algebra, and in fact, many first semester courses in linear algebra don't even talk about the SVD. Now, I think that's a bit of a pity because the SVD is not only very important, it has so many practical applications, it's also really illuminating. Once you understand the SVD, it really helps you understand how information is packed and layered into a matrix. Now, a complete understanding of the SVD, as you might imagine, takes a little bit more than a few minutes of introduction in a video. Nonetheless, I'm going to try to provide a conceptual overview of the SVD, as well as highlight one of the important applications in SVD in data compression. All right, so the big picture idea is to take a matrix. It can be a square matrix or a rectangular non-square matrix, and decompose this matrix into the product, the multiplication of three other matrices. So you see here is some matrix A, and this equals, so this is exactly equal to this matrix times this matrix times this matrix. Now, this matrix is often called matrix U, the letter U. This is often called V, capital letter V. And this matrix is often called sigma, the capital Greek character, which is the same as this character. So you can multiply these three matrices together, and that will reproduce exactly matrix A. Now, this matrix U provides basis vectors for the column space of A, so that's the columns of A. And this matrix V provides a basis for the row space of A, so that's the space that's created by combining all of the rows of this matrix. Now, the thing is that all the columns in this matrix and all the rows in this matrix are unit vectors. They are fixed to have a length of 1. Now, that means that they point in a specific direction, but they don't encode any length. They only encode directions. Now, the thing is, directions are one thing in a matrix, but the importance of those directions is encoded by these, the singular values. So these matrices encode directions but no magnitude, and the singular values encode magnitudes but no directions. And when you pair them together, these unit length vectors plus these magnitudes, then ultimately that tells you which are the most important directions in this matrix. And the thing about these directions is that is where the information in the matrix is embedded. Furthermore, these singular values are sorted from largest to smallest. And in fact, some of them will be 0. And any vectors that are associated with a singular value of 0 are in what's called the null space of the matrix. And if the matrix is full rank, then there is no null space. And if the matrix is reduced rank, then there is a null space, and then there will be 0-valued singular values. So this is really interesting from a compression perspective, because if you want to know what are the most important features in this matrix, then you just have to find the columns in matrix U and the row vectors in matrix V transpose that are associated with the largest singular values, and those are the most important features in the matrix. All right, so I hope that makes a little bit of sense for a big picture overview of the SVD. I think this will make a little bit more sense when we have a look in MATLAB. So what I'm going to do is import a picture of Einstein. It's a famous picture of Einstein. I think you'll recognize it. I'm using the function imread for image read. Now, initially, this is a three-dimensional matrix. It has, well, let me type this out so I can type whose. And we can see this matrix is 3 dimensions. So it's 405 pixels wide, 314 pixels tall. Actually, I think it's the other way around. It's 400 pixels high and 300 pixels wide, and 3. And this third dimension here corresponds to the RGB channels, or the different color channels. Now I'm going to use the function imShow to show this picture. So here you see the matrix represented in picture form. And you've probably seen this cute picture from Einstein before. All right, but the SVD uses only a flat matrix, so we want to squeeze out this third dimension, and I'm going to do that by averaging over the third dimension. So let's see what this looks like. Now you can see it's still 405 by 314, but there's no third dimension here. So I can make another image of this, ein flat. And whoa, that looks a little bit creepy almost, but that's just the color scale. So I can set this to be color map gray. And I think now this looks a little bit nicer. I'll also make the axis square. So now I'm going to compute the singular value decomposition of this matrix. You can see that gives us these three matrices. Actually, let me type whose again. So we have the original matrix that we're computing the SVD of. That's 405 by 314. And now I have these three matrices here. So U is 405 by 405, so that corresponds to the columns of this matrix. And then we have S, which is the matrix of singular values. That's actually the same size as the matrix. And then we have V, and that's 314 by 314. So that's a square matrix that corresponds to the number of rows in this original matrix. Okay, so I mentioned before that this matrix, which in the slides I called matrix A, and now it's variable ein flat, that can be exactly represented as the product of U times S times V transpose. But what I want to do here is create what's called a low rank approximation of the image. So first let's see what is the rank of this matrix. So the rank of ein flat is 314, which means it has the highest rank that it possibly can have. The highest rank that a matrix can have is the smaller of the number of rows and the number of columns. So what I do here is multiply not the entire matrices together, but only the first ith column. So the first, so only the first column, and then the first two columns, the first three columns, and so on. And what you're going to see is that this is a low rank approximation of this full rank matrix. And it's pretty interesting to see how Einstein becomes more and more recognizable as you add more features to this image. So let's see what that looks like. So here we have these different approximations. Now you'll notice that these are all the same size as the original matrix in terms of the number of pixels along each dimension. So this is the rank 1 approximation. This is basically looking for the single most important feature in this matrix, and that happens to be something that looks like this. Now this is clearly not recognizable as Albert Einstein. It's not even recognizable as a face. But that is, according to the singular value decomposition, the most important feature in this matrix. And then here is the two most important features added together. Now it still doesn't look like Einstein, but I think you can agree that it's starting to look like a face. And here we go. I think already by the first four important features, it clearly is a face, and it's starting to look a little bit like Einstein. All right, so the question is, how many layers, how many important feature directions in this matrix do we need to identify this as the picture of Albert Einstein? So that might be as few as 6 or 7, but certainly by 11 or 12, it's really obvious that there's not a whole lot of new information that's really being added when you get to rank 16 compared to rank 12. And that's pretty interesting because the rank of the full matrix is over 300, whereas we can get a really good approximation of this matrix using only rank 10. So this is very interesting from a compression perspective, because if you can represent all of the information in this original matrix, which is 314 rank, using a rank 10 matrix, then that's basically a 30-fold decrease in the amount of information that you need to represent this face. Now I can show you the relative importance of all these different singular vectors by looking at the diagonal of this S matrix, the sigma matrix. So first of all, let me show you what this sigma matrix looks like. It's barely recognizable, actually. It's a diagonal matrix, so all of these elements are 0, all of these elements are 0, and it might be a little more visible if I plot the log of this. Okay, so here you see all the singular values on the diagonal here. I just added EPS is a tiny number, and I just added that to avoid taking the log of 0 here. So let's just plot these numbers here and see what they look like. So I'm going to use the function diag to extract the diagonal elements of a matrix. And actually, let me plot it like this. Okay, so this is telling us that this first component, this first feature, is really important. It accounts for a lot of variance in the signal, but it's not terribly informative in terms of recognizing this as a face. But you can actually see when you look at, let me go back to this full image. So when you look at this, your brain is doing all kinds of computations and facial recognition and pattern recognition, memory and emotion, all sorts of things that your brain is doing when you look at this picture. But imagine you are a computer looking at this picture. What do you see immediately? What you see as the most prominent feature is that there's a lot of white here and there's a lot of darkness around the edges. So from a purely statistical perspective, this is the most prominent feature, that there's a lot of light colors here and dark colors in the periphery. And that's really what this first component reflects. Now we get to the next component, and the next component, the next component, and so on. And now you can see these components, these subsequent singular features, are getting smaller and smaller in importance, which means they're making less and less contributions to the recognition of the image. And what I was plotting here was, let's see, so x limits go from 0 up to 20. So I'm just changing the x limit here. So what we observed qualitatively looking at this series of pictures is that we can detect that this is Einstein sticking his tongue out by somewhere around 7 or 8 features. And then by the time we got up to, 14 or 15, we're not really adding any more information. So a lot of the other features after, around 16 are really just adding tiny, tiny little details and probably also a bit of noise, spackle noise. So let's see where those are here. So we found that the image becomes really recognizable after around 7 or 8 components, and you can see that's when this curve starts to flatten out. And we also decided that somewhere around here was where adding more features don't seem to make the picture much more recognizable. And you can see that these are all relatively small singular values, and they kind of flatten out. So thanks for watching. This was the big picture overview of linear algebra in approximately 1 hour. I think it ends up being a little bit over an hour. If you enjoyed this video and feel like you learned something from it, then please like this video and subscribe to this channel. And check in the comments sections for links to additional courses that you might also enjoy and find educational.